So let me first share the screen.
Good afternoon, everyone. We are privileged to introduce Professor Govind Pandey, sir, Dean Infrastructure and Planning, Madan Mohan Malviya, University of Technology, Gorakhpur. Professor Pandey is an excellent administrator, academician, and researcher. He completes his PhD in Environment Engineering from IIT Roorkee. He has very vast experience in the area of environmental engineering. It is very difficult to mention his accomplishment, but in brief, 63 research papers published in international journals, 3 books published, chaired and participated more than 100 national and international conferences. He is reviewer and editor of more than 8 referred journals. He is recipient of 11 national and international awards. He is accredited and recognized faculty member by International Accreditation Organization IAO, Houston, USA. Now over to you, sir. Please take the session. Thank you, sir.
Thank you very much, Pratibha. I am really grateful to you for a lucid introduction that you have given to me before I start my presentation to the learned participants here. I hope I am properly audible to everyone. Is it properly
Yes,
audible?
sir. Yes, sir. Your voice is audible and your screen is visible, sir.
Okay, good enough. So this afternoon I shall be sharing some of the facts and views relating to the management of water quality issues in India, because over the past several decades, we are looking into the resource planning at global level as well as at national level. And out of various natural resources, water resource is one of the most important ones, because you all know that this is an integral part of life, and our daily routine cannot progress, cannot go ahead without water. And because of the limited availability of water resource, and then the challenges relating to its fast utilization, or sometimes we say the depletion also, and then the quality issues, particularly because of the anthropogenic pollution, we are concerned both at global and national levels regarding its management. And when we talk about the management, the quality issues come first. In fact, the quality issues are not independent, rather they are also related indirectly and directly to the quantitative issues. So first of all, in fact, I shall present before you certain facts relating to the quantitative availability of the water resource, both the surface water and the groundwater. And then we shall look into what the quality challenges relating to water are. And then in the last segment of the lecture, we shall also look into the facts relating to the wastewater management in the country, and then what could be our perspectives and the management strategies to overcome the problem. So let me put it in slideshow mode if it is. So has this slide progress? Is it the second slide that is visible to you, or it is not visible to you? Second slide, contents of lecture on management of water quality issues in India. Is it visible?
Yes, sir, it is visible.
So these are the various points which I have included in the presentation for you, and maybe in a time span of about 1.5 hours, we shall try to sum it up. When we talk about the global scenario of water, it appears as if it is a world of salt, because if we look at the total global saltwater and freshwater estimates, so that reveals that out of the total water resource available globally, 97.5% is saltwater, which is mostly contained in seas and oceans, and only 2.5% is fresh water. Although there are certain variations in the estimates by certain other international bodies, some other international bodies say that the salt water content is 97.3% and freshwater content is 2.7%. But one thing that can be taken for granted is that most of the water resource that is available is salt water contained in seas, which is practically not suitable for human consumption. And out of that, fresh water, which is only about 2.5% of the entire resource, about 68.9% is contained in glaciers and permanent snow cover, which is again practically not available for human consumption. So almost 2/3 of the fresh water is in the form of glaciers and permanent snow cover, and only 1/3 is in the form of surface and groundwater, out of which only 0.3% is available in lakes and river storage, and about 30.8% is available in the form of groundwater, including soil moisture, swamp water, and permafrost water. So please note that the soil moisture or the swamp water or the permafrost water are again not available for human consumption. And one more thing that has to be noted, that with the present technology of groundwater harnessing, it has been possible for man to go up to a few kilometers in the depth of the earth, not more than that, and that too for water exploring, that exploration, it is only about a few hundred meters. So, and most of the groundwater which is available at the deeper depths is again inaccessible. So that is the scenario where we stand today. It is another pictorial presentation of the same view. I think the slide is progressing at your end.
No, sir.
Not progressing. Okay, let me skip the slideshow mode. Sometimes it happens, and I should go to the normal mode. Now, this may be visible to you. Is it visible now?
It is.
Right. So, out of this, the same scenario is shown a little bit more in detail. Out of, you can say, this fresh water in lakes and the rivers, only the water which is available is can be used for human consumption, but other modes like in the bodies of the plants and elements, or in the atmosphere, or in the soil moisture, where whatever water is available is practically unavailable for human consumption. This is a pictorial presentation of the hydrologic cycle on the left hand side, and then the a rough estimate of the Earth's reservoir of available water. If you look at that, out of the total fresh water, the groundwater is available in the form of 0.59% of the total water resource, and lakes 0.008%, and rivers 0.0008%. Right? Now you can just exclaim at the figures. In the form of soil moisture, more water is available than whatever water is flowing into rivers. Sometimes it may look very amazing, but that is the truth. So, and that soil moisture is practically not available for human consumption. It is for many other uses, but not for human consumption. Similarly, the water contained in the atmosphere and biosphere is also not available. So only a limited portion, that is 0.59% of groundwater in the form of groundwater in aquifers, 0.008% in lakes, and 0.0008% in rivers. If you sum up the entire three figures, it will be not more than 0.6%. So out of the total water resource that the God has given to us, only about less than 0.6% is practically available to human beings for various types of consumption and developmental needs. So that means water is not an abundant resource as of now, as we had been considering many times earlier, when we used to say that the money was flown like water in somebody's daughter's marriage. So now that water resource is no more an abundant resource. It is a scarce resource now globally. And when you look at the global scenario of water withdrawal, the situation is really very concerning, and in some regional perspectives, it is alarming too. You look at the global water withdrawal scenario in the year 1995, and then what it is going to be in the year 2025, that is about 3 years later. If you look at this world map, the deep blue tone is for such regions where the withdrawal is less than 10%, and the light blue is for such regions where the withdrawal is from 10 to 20%. Then light yellow is for the regions where the withdrawal is from 20 to 40%. And then deep yellow is for the regions where it is more than 40%. One thing which is conspicuous when you look at this world map is that the yellow portion is increasing, right? And the blue portion is decreasing. That means in many regions of the world, the global water withdrawal is increasing tremendously. If we look at specifically at India, now in 1995, Indian subcontinent lied in the consumption or withdrawal segment of 20 to 40%. But in the year 2025, it is likely to be in the segment of more than 40%. So that means here also the situation is going to be grim in the coming years. And when you look at the global water use and withdrawal and consumption together by various sectoral uses, like the use by agricultural sector or domestic sector or the industrial sector, or that water contained in reservoirs. One thing which is obvious from all the figures is that be it agriculture, be it domestic consumption, be it industry, the water consumption is increasing. Water withdrawal, there are three pictorial presentations. One is withdrawal, the other one is consumption, and the balance of the two, that is withdrawal minus consumption, is wastage. So the upper figure, if in all the three, is for withdrawal, and the middle one is for the consumption, and balance of the two is wastage. So you look at that in all the three figures, the withdrawal is increasing, that is number one. Secondly, consumption is also increasing, that is number two. But what is more alarming and point of concern is that the gap or the difference between withdrawal and consumption is widening. If you look at the figure from the year 1900, 1900, and then you look at the projected figures for the year 2025, that gap between the withdrawal and consumption, which is nothing but the wastage. So that is increasing, that is widening, right? Be it agricultural sector, be it domestic sector or industrial sector. But what is more visible here is that the wastage, even though it is not very high even though it is very high in the agricultural sector, but when you look at, compare it with the domestic sector and the industrial sector, the wastage is much higher. So then what we learned from here is that whatever global withdrawal we are making, we are not consuming that efficiently, right? We are not able to save water. Rather, the wastage is increasing like anything. So we have to control the wastage if we have to preserve the resource. Now, when you look at this map, river basin map of India, you find that India is a country where we receive water throughout the year, but most of the water, that is about 75% of the rainfall, we are receiving in the month of in the monsoon season, that is from July to September. So about 4,000 billion cubic meter of rainfall is received in India, out of which 75%, that is about 3,000 billion cubic meter, is received in monsoon season. And that too, on an average, there are only 40 rainy days when we receive the intense rain. On other days, we receive a very light or drizzling rain, or sometimes there is no rain. And but out of the total 4,000 billion cubic meter which is received a rainfall in the country, only 600 to 690 billion cubic meter is put to use so far. Remaining goes as wastage, goes into rivers, lakes, and other storage, surface water storage, and then it finally joins the oceans and seas. So then we have to catch the rain, right? Out of 4,000 billion cubic meter, we are able to catch only 600 to 690. Remaining is still flowing into the rivers and then ultimately joining the seas and oceans. So whatever agenda, that national agenda the government is emphasizing, catch the rain, is really rooted here. If you look at the national water quality policy of the year 2002, in fact, it emphasizes on the multi-sectoral integrated water resources development and management in the country. And as I have told you earlier also, India receives annual precipitation to the tune of about 4,000 billion cubic meter, out of which 75% are to the tune of 33,000 billion cubic meter is received in the month of in the monsoon month, that is from June to September. This is the rainfall map of India, where you can see that the maximum rainfall is shown in red tones. Deep red is maximum rainfall, and then deep green is minimum rainfall area. So there are some areas in Rajasthan and then Punjab and then Jammu and Kashmir, where particularly a larger portion of Ladakh region, and then in the northwestern region, where a very small or scanty rainfall is there. But there is a good portion where the red color tone is there, where good rainfall, maybe more than 2,000, 1,000 to say 4,000 millimeter of rain is generally received, or if sometimes more than 4,000 millimeters of rain also. But that yellow tone is a region which is also quite a good area in the country where the rainfall is not very high, not very low, sometimes average or below average. Certainly, where we stand here in the uh, most part of Himachal Pradesh or New Delhi or maybe Uttar Pradesh or Bihar or West Bengal, a good rainfall scenario is there. Then, if you look at the scenario critically about 1160, that is 1160 millimeter of rainfall, which is the long-term average annual rainfall for the country. It is highest anywhere in the world for a country of comparable size. That means whatever average rainfall we are having for a comparable size of the country elsewhere in the world, we stand the highest. That means nature has not done any injustice to us in terms of rainfall. We are receiving the maximum rainfall in the geographical area that we have. Certainly, there is a special variability. Like on one hand, the places like Jaisalmer in the west receive only about 150 millimeter of rain in the entire year. On the other hand, the places like Mosindram near Cherrapunji in Meghalaya in the northeast, the rainfall is about 11690 millimeters. And at that pace, daily rainfall, the highest daily rainfall is regarded as 1040 millimeters just in a day. So even though that monsoon period from June to September is spread over a period of 120 days, but generally there are 40 rainy days when we receive good rainfall in the country. When you look at the status of surface and groundwater resources, although India occupies 3.29 million square kilometer geographical area, which forms about 2.4% of the world's land area, it supports over 17% of the world's population. So on the other hand, we can say that we are having 1/50th of world's land and 1/25th of world's water resources. But we are supporting about 1/6 of world's population. And in addition to that 1/6 of world's human population, we are also supporting the livestock population of 500 million in the country, which is about 20% of the world's total livestock population. So that way, we require a lot of water resource to support the population needs. When we look at the availability of water resources in surface water and groundwater, the basin-wise average annual flow in Indian river system is about 1953 cubic kilometer, and the utilizable surface water resource of the country is 690 cubic kilometers. You can see out of 1953, only 690 we are able to use. The remaining is still flowing into rivers and lakes and ultimately joining the oceans. When we look at, on the other hand, the groundwater resources, about 342.43 billion cubic meter is the groundwater recharge from rainfall in the country, which is only about 8.56% of the total annual rainfall of the country. So recharge is very, very low. And if you add to it the augmentation from canal irrigation system, then that is about 89.46 cubic kilometer. So then it is about 431.89 cubic kilometer in total, which is around 10%. So that simply emphasizes the fact that we have to increase, we have to focus on increasing the groundwater recharge. And that is why nowadays there is an emphasis by the government of India and then many other, local bodies also, that we should go for rainwater harvesting and the groundwater recharge. So the region lies here. When you look at the water use in India, the sectoral water use scenario is such that irrigation had been using, that figure is for year 2000, at the start of the millennium. So 85%, and then for domestic it is 6.6%, industry it is 1.26%, and energy 1.3%, and other uses for 6.47%. But that pattern is now changing year by year. When you look at the annual water requirement for different uses in the years 2010, 2025, and 2050, you can have a comparative figure outlook. For example, in the irrigation sector, there are two types of estimates which are given. Low and high estimates are given for everyone. So for that year 2010, the irrigation required 78% of water. By the year 2025, it is likely to be 72%, and then by the year 2050, it is going to be 68%. That means irrigation water use over the years is going to come down. It is because of several reasons. One of the prominent reasons is that a lot of the agricultural land is being occupied for the developmental activities like construction of buildings, roads, and other infrastructure or industrial hubs. On the other hand, the water availability is also challenged, and therefore that irrigation water use is likely to decrease. For domestic sector, 6%, 7%, and 9%, that shows an increasing trend because there is an increasing trend in population, both the increase in human population and livestock population. So that is likely to increase over the years. For industries, 5%, 8%, and 7%. So it will be maybe more than 1.5 times by the year 2025, and then a little decrease is there because when the industry is not getting the raw resources, other resources, then its growth will be limited, so water requirement will also come down. But power 3%, 4%, and 6%. Inland navigation 1%, 1%, and 1%. Environment and energy requirement 1%, 1%, and 2%. Evaporation losses 6%, 6%, and 7% because of the climate change and the global warming. That evaporation losses are going to increase. So these are the points of concern in the global water requirement increase in the upcoming years. And when you plot these trends, maybe through a pie chart or through a bar chart, the situation emerges like this. And in the year 2025 and 2050, you can see that even though the major share is for irrigation, but then the domestic water requirement and industrial water requirement is also increasing at a very fast rate. And when this consumption is increasing, that means that per capita, because if you are using more water, so you'll be leaving only a limited water quantity for further consumption. So there is a very interesting norm, international norm, which says that if per capita water availability is less than 1,700 cubic meter per year, then the country is categorized as water stressed. And when it is less than 1,000 cubic meter per capita per year, then the country is classified as water scarce. If you look at the Indian scenario, in 1991, that per capita surface water availability was 2309, and in 2001 it was 1902. These figures are projected to reduce to 1401 in the year 2025 and 1191 in the year 2050. Now, 1401 is the figure which is likely to come up in the year 2025, which is pretty less than 1,700 cubic meter per year. That means by the year 2025, India is going to be a water-stressed country or water-stressed nation. And then by the year 2050, when the per capita water availability is going to reduce to 1191, even though it is a little more than 1,000 cubic meter per capita per year. And it may not be truly the water scarce nation in the year 2050, but that will be certainly heading to be a water scarce nation, if not in 1950, maybe in the year 1960 or so. So that is again a point of concern for our country. If you look at the increase in urban population, the trend is conspicuously visible here. And because the urban population is increasing, so urban water demand is also increasing, which is depicted in the form of bar chart at the bottom. And on the other hand, this is the population trend. When you look at the state-wise net water requirement in the year 2010, 2025, and 2050, you see that state-wide water requirement is also going to increase year by year. If you are interested for your own state, you can see that there is a definite trend of increase in the water requirement over the projected years. So, in addition to the quantitative figures, when you look at the qualitative figures, the major causes of water pollution in India are the domestic sewage, the industrial effluents, and the non-point sources of pollution, that is the diffuse pollution, which mostly comes from agricultural runoff. Now, when you look at the status of municipal wastewater treatment in the country, out of 423 class 1 cities and 499 class 2 towns, which together generate an estimated 61754 ml sewage, only 62 point, say you can say 37.1% is getting treated and 62.9% is still untreated, which is a major point of concern. Similarly, for industrial wastewater, which is about 14,000 ml, only about 60% treatment is there. And the biggest problem in the industrial wastewater management is that many a time the industries try to remain under default and they are trying to bypass the effluent without any treatment just to save money. So when you look at the status of sewage generation and treatment in the country, the sewage generation is that much the bigger ellipse, and then the sewage treatment capacity is the smallest ellipse, and the untreated sewage is the medium ellipse. So that means we have to strategize ourselves so that we are able to develop our generation capacity equal to the sewage generation capacity. And then in addition to that, point source solution, there are certain the non-point sources of pollution also, including the artificial fertilizers and the pesticides in many forms which are being used at the during the infection. So what I wanted to emphasize was that because of the discharge of the non-point sources of pollution into water bodies, the water quality is getting degraded. The state-wise percentage generation of sewage, this is quite an interesting pie chart. Like Maharashtra and Uttar Pradesh are the biggest polluters. They are generating the highest uh, quantity of sewage. There are other states like the Tamil Nadu, West Bengal, or the Gujarat, right, which still follow India, but whatever wastewater we are generating, that has to be treated. That is the biggest responsibility of the state. And from that point of view, the states like Maharashtra, Uttar Pradesh, Tamil Nadu, and West Bengal have to contribute very significantly to the collection, treatment, and disposal of the sewage. State-wise, union territory-wise sewage treatment plants are listed here. We will not go into much of these details. And then you look at the sewage generation and treatment scenario in the country. We have three types of common townships. One is the metropolitan cities, the other one is the class 1 cities, and then the third one is class 2 cities. In metropolitan cities, about 51% is getting treated, not more than that. In the class 1 cities, only about 32% is getting treated, not more than that. And in class 2 cities, only about 8% is getting treated. So what we can see here is one that we have to increase our pace of sewage treatment in all the cities, but we have to go with the increased efforts for particularly for class 2 cities where the treatment is only 8%, or class 1 cities where the treatment is only 32%. This is the scenario of water supply, wastewater generation, and treatment in class 1 cities, right? So the left one is for water supply, the middle one is for wastewater generation, and the right one is for treatment. So you look at the water demand that is increasing, and then wastewater generation is also increasing. But you look at the treatment is not picking up as much as the wastewater generation is increasing. So that is the gap which has to be filled in the coming years. This is for class 2 cities. Now this is different from the previous figure in the manner that the treatment is very, very low. So we have to focus our attention. If you look at these figures, we have to focus our attention on the class 2 cities to a very high extent, so that the treatment scenario improves. There are water quality issues which need to be addressed, which are classified in three categories. One is the common issues of surface and groundwater. The second one is the issues related to surface water only, and issues relating to groundwater only. So the pathogenic pollution or the salinity or the toxicity in the form of the micropollutants and the other industrial pollutants relate to the common issues of surface and groundwater both. Whereas for surface water, the issues are like eutrophication and oxygen depletion and the ecological health of the water body need to be addressed. And for groundwater, the parameters like fluoride or nitrate or arsenic or iron are important, and particularly in coastal areas, the seawater intrusion has also to be looked into because that may uh, refer to sometimes the additional chloride content in groundwater. Use-based uh, classification of surface water in India, or better to say, the designated best use-based classification (DBO). So you look at the table. There are 5 categories: A, B, C, D, and E. The best class is A, and the worst class is E. There are certain parameters which are listed in the primary water quality criteria, like pH is there, or POD is there, or COD is there, or dissolved oxygen is there, or the sodium absorption ratio is there, electrical conductivity is there. So we see that none of our Indian cities, when I say none means the pious cities like Ganga and Yamuna, are in full length in class A, quality class A. So now they are being preserved as class B rivers, not class A rivers. There are certain rivers like Brahmaputra and many other rivers in the northeast or in the Jammu and Kashmir and Madhya Pradesh, which are quite good in quality, which can be classified on the basis of these criteria. The drinking water standards, even though are prescribed in the country by Bureau of Indian Standards through IS 10500 2012, yet there are prescriptions by ICMR and CPHEEO also. But anyway, in the absence of any module, or in the absence of any descriptive suggestion, we always go by the parameters which are prescribed by the Bureau of Indian Standards. And to keep our water bodies in the state that you can derive your drinking water supplies with the maximum care for safety, we go for the water quality monitoring. And there are certain water quality monitoring objectives, like sometimes we go for monitoring, then sometimes some other time we go for survey work, some other time we go for the so for rational planning and pollution control strategies and their prioritization, to assess nature and extent of pollution control needed in different water bodies or their part, to evaluate effectiveness of pollution control measures already in existence, to evaluate water quality trend over a period of time, to assess assimilative capacity of water body, thereby reducing cost in pollution control, to understand the environmental fate of different pollutants, and to assess the fitness of water for different uses, could be several water quality monitoring objectives. And when you have assessment, so monitoring is one part of assessment. There are other parts like surveillance and the survey. The difference between the three is that in monitoring, we have the long-term standardized measurements in order to define status or trends, whereas in surveillance, continuous specific measurements for the purpose of water quality management and operational activities are there. And in survey, a finite duration intensive program to measure for a specific purpose, right? And when you set the objectives of water quality for monitoring, surveillance, and survey, so in monitoring, we have three types of monitoring. One is the baseline monitoring, which is for natural background concentrations. The other one is trend monitoring for the detection of changes over time due to anthropogenic influence. And then the third one is flux, which is considered for the calculation of load and the calculation of mass flux. In surveillance, we have two types. One is water use and the other one is for pollution control. In water use, we check that water is fit for use, and in pollution control, we check the effects of discharges and also check the water quality standards. And in survey, again, we have two types. One is the classification, which is done for the classification of the reach of a water body. And the second one is management and research, which is done for the investigation of pollution and need for corrective measures, special interest, and filling in the knowledge gaps. And when you look at the National Water Quality Monitoring Network taken up by Central Pollution Control Board, there are about 445 rivers, 154 lakes, 12 tanks, 78 ponds, 41 creeks and seawater, 25 canals, 45 drains, 10 water treatment plants, that is groundwater treatment plants, 807 wells, and among the 2,500 stations, 1275 are on rivers, 190 on lakes, 45 on drains, 41 on canals, 12 on tanks, 41 on creeks and seawater, 79 on ponds, 10 water treatment plants, groundwater, and 807 for generation stations. When we look at the parameters for national water quality monitoring, so that has several groups. One is the group of 4 parameters, wherein 9 parameters are included. Then there are field observations of 7 types, 7 parameters. Then general parameters, 19 numbers. The bio monitoring parameters, and then the trace metals and pesticides. When you look at the data over the years for the quality of river Ganges and river Yamuna, the monitoring results reflect that organic matter and bacterial population of fecal origin continue to dominate the water pollution problem in India. And the pathogenic pollution as reflected through indicators, that is total coliforms and fecal coliforms, and organic matter as reflected through BOD, and salinity as reflected through conductivity and other inorganic parameters and nutrients as reflected through nitrates and phosphates. When you look at the water quality trend, the organic and bacterial contamination are continued to be critical in water bodies. That is one trend. And this is mainly due to the discharge of domestic wastewater, mostly in untreated form, from the urban centers of the country. Secondly, the receiving water bodies also do not have adequate water for dilution, and therefore the oxygen demand and bacterial pollution is increasing day by day. This is the state-wise riverine length in kilometers under different levels of pollution. You look at this table, state is on the left-hand side column, left column. Then on the right-hand side, you have got 4 columns. First 3 columns are for the rivers which have the biochemical oxygen demand BOD either less than 3 or from 3 to 6 or more than 6 milligrams per liter. Less than 3 is considered to be relatively clean. 3 to 6 is considered to be moderately polluted, and more than 6 is considered to be severely polluted. So in Jammu and Kashmir, you have got the total riverine length of 2291, and the entire length is relatively clean. None is moderately polluted or severely polluted. Himachal Pradesh, out of 1095, 1076 is relatively clean, and only 19 is severely polluted. But you look at Uttar Pradesh, out of 5619 total kilometer length of rivers, only 2473 kilometers is relatively clean. That is even less than 40%, 50% is relatively clean. And 1966 kilometers are in the range 3 to 6 milligrams per liter of BOD, and 1180 kilometers are in the range greater than 6 milligrams per liter of BOD, that is severely polluted. And if you look at the total scenario of the country, you find that out of the total riverine length in the country, 45043 kilometers, 30266 is relatively clean, 8691 is moderately polluted, and 6086 is severely polluted. Right? So about 2/3 is relatively clean, and 1/3 is either moderately polluted or severely polluted. This is the river basin-wise riverine length under different levels of pollution. Like for Ganga River, you can see the total riverine length is 12690 kilometers. It is, please mind that this is not the length of River Ganga only. This includes the length of River Ganga and length of all its tributaries together. So out of 12690 kilometers, 7318 is relatively clean, and remaining 3612 is moderately polluted, and 1760 is severely polluted. But on the contrary, look at River Brahmaputra. Out of its entire riverine length of 5013 kilometers, it is relatively clean, and none segment is relatively moderately polluted or severely polluted. There are rivers like you can say Subarnrekha. Out of 289, only 79 kilometer is left as relatively clean, and 120 and 90 kilometers are either moderately polluted or severely polluted. So same thing is true with the other rivers like Mahanadi, Godavari, and when you again look at the total riverine length, it is the situation like this, right? When you look at the water quality status, based on the analysis of 10 years data with respect to BOD values as indicator of high organic pollution, the severely polluted riverine length is 6086, which is about 14% of the river percentage, and moderately polluted length is 8691 kilometer, which is about 19% of the riverine length percentage, and about 67% is relatively clean. When you look at the total riverine length under different levels of pollution, it is shown through a pie chart here. Total riverine length under different water quality status is state-wise is given here. That is yellow or the blank is relatively clean, then brown is moderately polluted, BOD 3 to 6 milligrams per liter, and blue is the tone for severely polluted, that is BOD greater than 6 milligrams per liter. Look at the state of Maharashtra here. Only a very small segment is left which is relatively clean. Otherwise, either it is moderately polluted or severely polluted, right? Look at Odisha. Odisha also is in a similar situation, right? So look at Bihar. So here we have a grim situation. Look at Uttar Pradesh. Even a little more than 50% of the riverine length is either under the moderate pollution or the severe pollution. But there are states like Jammu and Kashmir or Himachal Pradesh or the northeastern states like Nagaland or Manipur or Tripura or Sikkim or Meghalaya, where none of the pollutants would affect the river water quality significantly. This is the total river basin-wise riverine length under different level of pollution. Look at river Ganga, right? A little less than 50% is either moderately or severely polluted. But look at river Brahmaputra, which is not at all severely or moderately polluted. But look at river Subarnarekha, very severely polluted, right? Look at river Ghaggar, very severely polluted, right? So that has to be looked into very seriously. Then this shows the state-wise perennial riverine length in India. If you look at the states where these bar charts are higher enough, like Uttar Pradesh or the Madhya Pradesh or the Andhra Pradesh or Maharashtra or the Karnataka or Tamil Nadu, Assam or the Jammu and Kashmir, where the nature has gifted a good riverine length. On the contrary, there are states like Delhi or Goa or Mizoram where the riverine length is not very high. Even in the state of Haryana, that riverine length is not very high. So those states which are blessed with the higher riverine lengths have a greater responsibility also on their shoulders to preserve the water quality in the rivers and to keep them pollution free. The Central Pollution Control Board has identified over the years the polluted water bodies or the stretches. It had identified 10 polluted stretches in the year way back in 1988-89, which increased to 37 during 1992-93, 86 in 2003, 178 in 2007, 275 in 2014. And now it is expected to be approaching a little less than 5. So that is a point of concern that in spite of our all attempts, the number of polluted stretches in the country is increasing, which is really very alarming. This is the state-wise location of the polluted stretches in rivers and lakes, right? So you can see, like in Maharashtra, there are most number of polluted stretches, 15 in number, right? Uttar Pradesh, 8 in number, Gujarat, 10 in number, right? Karnataka, 6 in number, right? So Andhra Pradesh, 8 in number, total 86 on the number of water bodies and 71 years. Okay. Now, river-wise polluted stretches are listed here. On Godavari, there are 2 stretches, right? On Ganga, there are 3 stretches. Yamuna, there are 3 stretches, right? So, Ganga, there are 2 stretches, and Gomti, there is 1 stretch. There are a total number of 71 stretches. This is the list of polluted water stretches across the country in all the states, starting from Andhra Pradesh. The name of the river is written here. You can just have a quick glance at these tables. So the name of the river is written, the name of the polluted district is written from where to where, and then the source or town is also listed, and the critical parameters are also listed. Like in Andhra Pradesh, in the river Godavari, it is the name of the polluted district is from Polavaram to downstream of Rajamundry, and the source town is Rajamundry and Polavaram State Sewage. VOD is about 6 to 12 milligrams per liter. So same thing goes, you come across the Andhra Pradesh, Assam, Delhi. Delhi, you can have the rivers Yamuna from Wazirabad to Okla. That is industrial and domestic waste from Delhi that is coming, and the VOD is 6 to 77 milligrams per liter. And then we have got Jharkhand, Gujarat, then Haryana, Himachal Pradesh, then Karnataka, Madhya Pradesh, Maharashtra, then Punjab, Rajasthan, Tamil Nadu, Sikkim, Uttar Pradesh, and West Bengal. You see in the Uttar Pradesh, Yamuna, Hindan, Western Kali, Buri Yamuna, Kali Nadi, Eastern, Gomti, and Ganga rivers. So that whole list is available. Now then, for your information, I shall very quickly lay down the experiences that we have seen from the Ganga Action Plan or the Yamuna Action Plan. You know, the Ganga Action Plan was implemented in the country way back in the year 1984-85. And ever since then, lot many sewage treatment plants have been built, lot many drains, discharging into river Ganga and Yamuna, they have been capped, they have been tapped, and they are being treated. And then there was an eye on the water quality monitoring of the river Ganga and Yamuna also. So if you look at the river water quality monitoring results, it gives us an insight into what lesson we should learn from these. This is the water quality trend of river Ganga from the year 2002 to 2011. There are three trends which are shown here. One is the minimum trend, which is in the form of pink diamonds. And then the other one is mean, which is in the form of the red rectangles. And then the third one is in the form of maximum values, which is in the form of the yellow triangles. If you look at the minimum POD, it is more or less the same. It is not changed. You look at the mean VOD, again it has not changed. Rather, it was 2.5 in the year 2002, and now it is 3.3 in the year 2011. So instead of decreasing, it has increased. In many other years, it was having even the value like 3 or 2.9. So, and when you look at the maximum figure, then in the maximum figure also there is not very significant change. So what I can say is that it shows as if it is like that only. And same thing is visible here again in the water quality trend analysis of river Yamuna. The minimum is like that. The mean value is again like that. In the year 2002 also it was 7, and in the year 2011 also it is 7. No change. In certain mid years it was even 9.2, 9.9 also, right? And same thing is for maximum. In the year 2002 it was 36, and in the year 2011 it is 41. And in some other years it was even higher, like 144 or 103 or 84. So that means that in spite of the best efforts that have been made ever since 1984-85, much of the targets have not been achieved. Then we have to look into this, why it could not materialize and how we can take it up further. And the experiences from the Ganga Action Plan have shown that the sewage collection system is either partial or non-existent in many of the towns and cities located on the bank of river Ganga. Then interception and diversion of drains and down monsoon runoff is necessary. The sewage treatment plants which have been installed on the bank of river Ganga, the operation and maintenance has to be done properly. For that, the operational cost and operational staff is to be there. Power supply is a problem at many places, that the treatment plants are either they are not getting continuous power supply, or sometimes the power backup, if it is there, then the power backup is not properly functional. Like if diesel power generator sets are there and there is no diesel available. So such type of problems are there. And then there is a problem of availability of skilled manpower for running and operating these treatment plants. That is also has to be properly looked into. When we look at the experiences from industries, you find that there are high organic loads, particularly from distilleries, and that is why nowadays the distilleries have been allowed to operate only on zero liquid discharge ZLD. They are not allowed to discharge any of their effluents outside. They have to run under zero liquid discharge. Then industrial effluents are sometimes also have high TDS, particularly the effluents coming from pharmaceutical, pesticide, rayon dye and dye intermediate industries. And for small scale industries, the problem is that sometimes they are located in residential areas also, and they have inadequate resources and skill, and they are not able to have their own treatment plants. And for that, generally, the suggestion is that there should be a common effluent treatment plant (CETP) for a cluster of small scale or medium scale industries. But then there are problems with common effluent treatment plants also, particularly when you have uh, uh, the vehicle for running it, right? A special purpose vehicle or SPV. So for proper functioning of SPV, you have to take into consideration certain points which involve the parties which are responsible for polluting. And if you go by the polluter pays principle and collect the dues from the parties, concerned parties, you can manage the CTPs very well. Otherwise, CTPs are also under problem if they are not managed well. The government of India started integrated Ganga conservation mission in the title Namami Gange way back in the year 2014-15, and in the union budget that integrated Ganga conservation called Namami Gange, the amount was allocated. In fact, there are 2037 crores for this purpose had been allocated. And in addition to that, about 100 crores had been allocated for development of ghats and beautification of river fronts at various places along river Ganga. And in fact, they have two main things under consideration. One is the Avral Dhara and the other one is the Nirmal Dhara. So under the Avral Dhara concept, they try to maintain the discharge of the river, and if somewhere the discharge is reducing, they supplement that discharge. And in the Nirmal Dhara concept, they try to intercept the trails discharging into these rivers and treat that properly and try to keep the river water quality under the surveillance so that it doesn't degrade further. So that way they ensure the Avral Dhara also. Then assessment of groundwater quality in metro cities again is a problem, and because groundwater is the main source of drinking water in the country, and groundwater quality is being degraded gradually in large urban centers, critically. And although the ministry is, doing as much as possible, it is important to monitor the groundwater quality at various places in the country. And CPCB has included in its monitoring network around 200 stations for this purpose. And some common groundwater contaminants like the salinity, chlorides, nitrates, iron, coliform, arsenic or selenium, and micropollutants and pesticides and toxic metals have been included for groundwater monitoring. Then there are legislative measures also which are available for the water quality management, including the legal and institutional provisions laid down in Water Act of 1974 and Environment Protection Act of 1986 and National Water Policy of 2002. Then there are technical provisions which are being implemented through the National River Action Plan, the Environmental Impact Assessment, then pollution control in small scale industries, charters on corporate responsibility and environmental protection, special drives for industries discharging into rivers and lakes, and incentives for control of pollution. Now, certainly there are certain constraints also in implementation of water quality management plans in urban areas, which include the water scarcity, because if there is no water, in the trouble, inadequate resources with local authorities. They want to do much, but they do not have money. Then polluter pays principle. Polluter always wants that somebody else should pay for him or her. So that is also sometimes a constraint. High organic and dissolved solid bearing industrial waste. Large number of small scale industries where the CTP, well operated and well run CTP could be a good option. Operation and maintenance of treatment facilities created and the characteristics of effluents. And under the National River Action Plan, the number of towns which have been covered for this purpose is around 156, including 74 on the bank of river Ganges, 21 on the bank of river Yamuna, and many other towns on various other rivers. When we look at the water recycling and reuse scenario, which is the need of the hour, as of now only 30% of India's urban wastewater is recycled. And the apathy with regard to sewage treatment plants lies in the fact that those in urban spaces are neither properly financed nor designed. A consumption of 3,420 million liters per day leads to wastewater generation, as in Delhi, of over 2,600 MLD. Of this, only 1,600 MLD is treated and 338 MLD is reused. Mumbai is worse, according to officials in the Municipal Corporation of Greater Mumbai. Out of supply of 3750 MLD, 2300 to 2400 MLD goes into the sea almost untreated. So that is a very, very bad scenario. And if you do not recycle and reuse, the poor water availability will be there, and with that will render poor public health, increasing cost of water supply, and then that may also lead to long distance transportation with elevations, particularly in hill areas, poor economic performance of urban local bodies, and interstate disputes on resource allocation, as it has been many times with the Tamil Nadu and Karnataka, in which the intervention of the apex court of the country was also there, and then unsustainable growth is another problem. The way forward is to provide incentives to industries and agencies using reclaimed water to address legal and institutional issues, to develop a state-specific reuse guidance document, and to promote recycle and reuse through educational and public awareness programs like these for non-potable and indirect potable applications, and to develop funding alternatives for reuse projects. And when we come to conclude the discussion, we find that to preserve our water and environment, we need to make systematic changes in the way we grow our food, manufacture the goods, and dispose of the waste. If pollution by agriculture is reduced, it would improve water quality and would also eliminate cost incurred for treatment of diseases. Municipalities and industries need to carefully treat their waste discharges. Manufacturers should reduce water pollution by reusing materials and chemicals and switching over to less toxic alternatives. Also, there is a need to encourage reductions or replacement of toxic chemicals, possibly through fiscal measures. Efforts should be made to restore landscapes and ecosystems, to protect water quality and aquatic and wildlife more efficiently, and for maintaining the quality of fresh water, sustainable water quality management strategies are required to be evolved and implemented. The recycle and reuse of wastewater should be encouraged, and finally, the rainwater harvesting and artificial recharge of groundwater should be taken up on high priority. So these are the various important issues that relate to the management of water resources and the water quality issues in the country. With this, I thank you all for a very patient hearing. Now, you may have your queries or questions if any. Pratima. Pratima, are you able to hear me?
Hello?
Now,
Yes. Yes, sir. Thank you, sir.
The forum is open for any queries or questions or discussion. If the participants have any queries or questions or suggestions or observations, they are most welcome. If there are no queries, then I think you should thank the participants for patient hearing, and then we can conclude the session.
I am audible, sir.
You're quite properly audible.
Okay, sir. Thank you, sir. If anyone has any query, please come forward. I think, sir, there is no question, sir. If we receive any query or question, sir, we have sent to
Yes.
you.
Thank you, Pratibha, and
Thank you,
thanks
sir.
everyone for a patient hearing.
Thank you so much, sir, for your sharing your knowledge and for your time. Thank you so much, sir. Could I close the session, sir?
Of course, most welcome, most welcome.
Thank you, sir. Thank you.
Thank you so much, also. Thank you so much.